Johnny here with Simpson Math. In this video, I want to talk about how the behavior theorem applies to a second derivative. So we're still under this umbrella of curve sketching and calculus, and today we're going to be talking about concavity and inflection points. So let's just go back to something we're familiar with, the derivative function based off of a original function. So here I've got f, just some original function, f. And I notice at a I turn around and at b I turn around. So that means on my first derivative, I was negative up until a. So my original function was decreasing up until a. On the interval a to b, my derivative is all positive, meaning from a to b on my original function, I'm always increasing. And then beyond b, I am negative, so beyond b, I am decreasing. And I've got the behavior theorem for the first derivative written there, and we just noticed last time that the roots of the first derivative are where those local extrema occur, where those turnaround points occur. So I'm going to go further, and I'm going to now take a second derivative. So I'm going to take the first derivative of the first derivative. So I'm just looking at those tangent values, and I see that I start off positive and high, and I get lower and lower and lower. I get 0, a slope of 0 when my x is 0, and then I'm negative, and I get deeper and deeper into the negatives. So I think this quadratic-looking function will end up linear with a negative slope. Okay, I'd like to talk about how the second derivative relates to the original function. So, up until 0, the second derivative is always positive. So back to my original function, that is everything up until 0, that U shape. And then at B, that behavior changed, and now everything is below 0. Everything is negative after 0. On my original function after 0, everything looks like this. So now I have a upside down U shape. Any thoughts? It seems that at 0, when I went from positive to negative on my second derivative, at 0 on my original graph, that's where the concavity changed. I went from being concave up to concave down. So the roots of a second derivative are inflection points, or they can be inflection points. So I was just writing down the behavior theorem for the second derivative test. If the second derivative is less than 0, then the original function is concave down on that same interval. If the second derivative is positive, then the original function is concave up. And we call the point where the concavity changes an inflection point. So when we're sketching out these graphs, it would help to know where does the function change from being concave down to concave up. We want to find and plot those inflection points. So we're just going to continue building with what we've already learned, and our next basically step is to go off and test concavity, and then if there is a change in concavity, then we want to know where we want to find the actual point. Similar to the first derivative behavior theorem. All right, let's just jump straight into it. I've got this example, it's some cubic, and I say prove 2, 4, that point, is a point of inflection. So here's the function, and I want to prove that that point is actually a point of inflection. To prove it, I would need to somehow show that there is a change in concavity from up to down or down to up at the x value 2, and that 2, 4 is the point that that occurs. So I think I'm just going to apply this second derivative behavior theorem. So first things first, I'm going to go off and find a first derivative. F prime, using some power rules, 3x squared minus 12x plus 9. Here, I could find roots, but that would be talking about turnaround points, or local extrema, maxima. I'm going to continue with the second derivative. 6x minus 12. Just like our example, we had a cubic that went down to a quadratic that is now linear. If there is a change in concavity, it'll happen at new domain restrictions and at roots. So there's no domain problems here. This was a polynomial to begin with. It's a line now. Domain here is all real numbers. Domain to begin with was all real numbers. No problems. So the inflection points, these critical values, will only occur now at the roots of the second derivative. So I'm going to set this function equal to 0. Solve. And I get a critical value at x equals 2. So if I want to test behavior, this is where I put the critical value on a number line summary. So I'm just going to draw a little number line, place 2 on there somewhere, and then what I would like to do is test values below and above. 0 is probably the easiest, below 2, and then I'll choose 3 just above 2. And again, I'm going to be testing the second derivative. So my goal here is I want to know, am I positive and therefore concave up? Or if I plug in a number, do I get a negative and therefore I'm concave down? So this function, I know, has an unrestricted domain from negative infinity to positive infinity. There's only one place where behavior may change, and it's at 2. If there is no change in behavior, then I'm always going to be concave up or always concave down. So when I test these values, if I get both negative, then I'm always concave down. If 2 is a change in behavior, so I'll go from like concave down to concave up, then I've got a change in behavior, and we call that point an inflection point, where that concavity changes. All right, let's test it. I'm throwing this into a second derivative. I'm testing the second derivative. I'll plug in 0. It should be easy. 0 kills the 6. I'm left with negative 12. What I got was a negative number. If f double prime is negative, then the original f must have been concave down. That's my symbol for concave down. I'm now going to test 3. 6 times 3 minus 12. 18 minus 12 is 6. What I really care about here is the fact that it is positive. So I am concave up, like a cup. So yes, there is change in behavior when x equals 2, meaning I have an inflection point when x equals 2. If I want to actually find the point, I go back to my original function. The original function is an xy machine. If I plug in x, it should spit out a y, a coordinate. I'm just saying here, yes, there's a change in concavity. That means we've got an inflection point. When x is 2, if I want to find the actual point, I'll go back to the original and just shove it in. 2 cubed minus 6 times 2 squared plus 9 times 2 plus 2 just some arithmetic. This is the hardest part, probably. 4 times 6 is 24. 28 minus 24 is 4. So yes, 2, 4 is a point of inflection. So as I'm graphing the original function, I can add that to my list. I've already talked about domain, asymptotes, where it's increasing and decreasing, plotted those points, and now I want to know, well, where does the concavity change? What happens at 2, 4? Perfect. All right. Hope that helped. See you in the next video.